Hello, and thanks for using TickBoom. In this question, we've got this diagram here, and we're told that if we're starting from point A in the bottom left-hand corner, we then need to visit the line CD, then come back to the line AD, then come up to the line CD again, and then finally arrive at point B. What is the shortest possible distance we can travel? So the first thing to note is that as a general rule, the shortest possible distance between 2 points is a straight line. So you'll see that in each of these movements, we're always dealing in a straight line. So the question becomes, how can we tackle this without having to deal with a whole bunch of complex triangular calculations? So at first glance, this looks like a trigonometry question, and it is at the end of the day. But actually there's a creative technique that we can use that allows us to transform what looks like quite a lot of complex triangles into just one very simple triangle. So to get started, what I'll do is I'll draw up this starting diagram that we're given. So I'll just come down, we're told that this first line has a length of 5, and then we're told this line has a length of 6, then we come across with a length of 1, and then it's all connected with the diagonal. So that's the diagram we're given. Essentially, that's the polygon as it's described. Now, the trick here, the kind of unique or creative way to look at this is to think, what if I can redraw this polygon as if it had a mirror image? And if I do that 3 more times, can that help us with tackling this problem? So what I'll do is I'll use a different color. So we'll draw, again, a line with a length of 6. So that's got a line with a length of 6. And then we'll come up same height. So that's got a length of 5, then a length of 1, and then we connect. So you'll see there what I've done is I've simply drawn the mirror image. Now what I'll do is maybe I'll turn the book around, and then in another color again, I'll draw yet another mirror image. So we'll come out here by a length of 1, then we'll come down, and that's length of 5, and then we'll come across, and that's a length of 6, and obviously we've got this same diagonal over here. Then I'll turn my book around one more time. And my last color, we'll draw a line with a length of 1, a line with a length of 5, and then there's also this line here, which has a length of 6, and then the diagonal. If I turn my book back around, what I've done there is I've recreated this polygon, but in each time doing it somewhat of a mirror image. So for each of these diagrams, we're dealing with the same length of lines, but now what we can do is we can start to look at a unique way of dealing with the fact that we're starting here from point A, and I'll label these A, B, C, each of these points, and then point D. That's what we're given. And we're told that we're going to go from point A over to the line CD. See, this is line CD. Then from there we're coming back to the line AD. Then from there we're coming back up to the line CD. And from there we're going over to the point B. So we've got 4 movements, 1, 2, 3, 4. And notice I've drawn 4 versions of this polygon, 1, 2, 3, 4. And there's the little hint. We've got 4 movements and 4 mirror images. So notice here I'm going from the bottom corner over to the long diagonal. That's movement 1. Movement 2 is I'm going from the long diagonal down to the bottom of the polygon, or the line with length 6. Notice in this red version, if I continue this line forward, so instead of bouncing off this long line, I carry straight through it. Notice there I'm moving from the long diagonal to the line of length 6. So long diagonal to line of length 6, long diagonal to line of length 6. So from there I know that that line, the length of that line will be the same as the length of that line. Those two will match. Because in these identical diagrams, we're moving from the same point to the same point. Now, if I continue that on again, what I'm doing here is I'm moving from the line of length 6 over to the long diagonal. And that's actually what we're doing in our third movement, the line of length 6 up to the long diagonal. So again, this line and this line will have the same length. And then finally, if I go from here to here, I'm moving from the long diagonal over to the corner. And that's what's happening here. I'm moving from the long diagonal over to the corner. So again, this line and this line will have the same length. So what we've got now is an interesting situation where the total length of these 4 lines is the same as the total length of this one long line from this bottom corner all the way to this corner. And notice, if I just focus on that, what we're really looking at here is one big right-angled triangle. And you may know from Pythagoras' theorem that if you have any right-angled triangle, and if you label the sides A, B, and C, what we know is C squared is equal to A squared plus B squared. That's Pythagoras' theorem there. So if we now use that same rule, what we can get here is that the length of our line squared, so the length of this one long line, which we know is the same as all 4 movements, that squared is going to be equal to the length of this whole thing, which is 6 plus 6 squared, plus the length of this side here, which is 5 squared. So I'll just get my calculator. What we're keying in is 6 plus 6, or 12 squared, plus 5 squared is equal to 169. And that means that the length is equal to the square root of 169, which is equal to 13. And that's the answer. So there you've seen what looked like quite a tricky question, and it is. I mean, that would have been quite difficult to do all the calculations with trying to think about all the angles that you'd be dealing with to try and then determine the lengths. I'm not even sure how you would go about doing that, or whether you would have even had enough information. It's possible. But just through a little creative thinking, we've been able to convert what looked like a difficult problem into a fairly simple problem where we can use a fairly simple solution, being Pythagoras' theorem. So hopefully you found that helpful. If you were to encounter a question like this on an exam, I mean, that would be a fairly hard exam that you'd be tackling there, because this requires both knowledge of the math and also a level of creativity But like I often say, questions like this, it all comes down to practice. Once you've seen a few of them and you've learned that this is a possible technique, then hopefully your chances of knowing what to do when encountered with another question like this, hopefully your chances are increased of being able to work out a good way to go about it. So again, hopefully you found that helpful, and tick boom.